So our course is power electronics, and today's topic is DC to AC converter. That is also can be known as inverters. So we will go through this topic in today's lecture. Already we have covered two types of converter. One was rectifier, and the other in the previous class we have covered the DC to DC converters, buck converter, boost converter, or also can be known as choppers. So in today's lecture we will go through inverter. They can be known as DC to AC converters. So it's today's objective that we will cover different types of DC to AC converters. So what is actually an inverter, or what are DC to AC converter? So inverter are actually AC converter used to convert. Their input is actually DC, and their output is actually sinusoidal AC. But the output is variable. The output frequency is variable, and the output amplitude is variable. So DC to AC converters are actually DC to DC converters are actually those types of converters that convert their DC to AC. Their input is DC voltage and their output is AC. So the output AC that we are getting, so its frequency will be variable and its amplitude will be variable. The block shows a block diagram of the converter that its input is DC voltage and DC current, and its output is AC current and AC voltage. So it can be variable frequency and variable amplitude. Where they are using application of inverter, so they are used everywhere. They can be used in AC drives, they can be used in induction heating, in different aircrafts power supplies, in the UPS that are actually used in homes and computers, in the high voltage DC transmission line, they can be used over there. So it's the application of inverter, that if we are using a solar panel or battery bank, and we are getting power from it, and we want to convert it to AC. So an inverter is required in order to convert this DC voltage into AC. Broadly, the inverters are classified into two types of category. One is the VSI and the other is CSI. The VSI is the actually voltage source in inverter, and it actually shows that in VSI there is that one inverter in which the DC source has small or negligible impedance, where in the CSI the it comes with adjustable current, but the DC source from a DC source, and its impedance is actually high. So it's the difference between the VSI and the CSI. In the VSI, the impedance is negligible, where in the CSI the impedance is actually high. Okay, so the output voltage of an inverter, the output voltage of an inverter is rectilinear in nature, and therefore contain harmonics. Harmonic reduce the efficiency and may have adverse effect on the load. Harmonics reduction can be achieved by filtering or by using harmonic elimination technique. Whenever we convert the DC voltage into AC voltage, so we are not getting paired AC voltage. There are some of the harmonics, then we have to use the Fourier series, and we have to extract its the first fundamental frequency, and we then filter out its first fundamental frequency. By here we get the actual desired AC voltage. So we will actually define these steps in the previous slides, that what type of output we are actually getting, which techniques can we use, and how we can eliminate these harmonics in order to achieve our required output. So inverters can be classified into square wave inverter or PWM inverter. So further, there are single phase inverters, three phase inverter. In single phase, we have center tap inverter, full bridge inverter. In three phase, we have 180 conduction mode inverter and 120-degree conduction mode. So in inverters, actually diodes and thyristors are actually used, and depending upon the load, if the load is resistive, then we are required one type of conduction mode, and if the load is So if the load is resistive, then one type of conduction mode is required. But if the load changes to inductive, then the conduction cycle or duration of the thyristor changes. Its effect will be later on. We will go through it. That what's the effect of load if it changes, and what type of strategy is required for this type. So first of all, this is the half bridge inverter. So it can be also known as inverter leg. So it's the basic building block for a full bridge or three phase or high order, because these half bridges are used in further or in the full bridge, where G is the center point. Both capacitors have the same value, thus the DC length is equally split into two. The top and bottom switch can become complementary. If the top switch is closed or on, the bottom switch must be off. So what are the switches actually? The switches can be thyristors, or that can be uh, some other thing like MOSFET, but they should be controlled devices. What actually happens if we go through its operation? The input is DC voltage. So first of all, if the this switch and this switch are off, it means they are reverse bias, or if they are not working, or if they are thyristor and the gate pulse is not required, so no current will flow through this. So what we are actually observing, where is our output? The output is actually across the load. That is actually RL. So we are, if we connect oscilloscope over here, or we are observing our output over here. So the DC voltage is over here. These switches are off, so 0 volts will be here. No current flows, so no voltage is absorbed over here. But if we on this switch, if this switch is on, the current will go through this, will go through this path and through this capacitor, and it will charge, and thus the path is completed. So what we will get a positive cycle, and its duration will be for how much time? Its duration will be like that for how much time the switch is on. If the switch is on for, let's suppose if suppose for 0.5 millisecond, so it means that for half duration the switch S1 is on, but the S2 is off at that time. But if we turn off this switch, or if it is a thyristor and we turn off it, and we turn on, and we provide a firing pulse to this thyristor, and it turns on. So now what will happen? Now the current will flow through this path. Now the current will flow through this C1 capacitor, through this resistance, and through this, because this path is closed. So the only path that is available for the current flow is through the capacitor C1, through the load resistance, and through this S2 switch. So in the first case, the current was flowing through S1 and through the load from positive to negative. That's why the output cycle was positive. But in the second part, when the switch 1 is off but the S2 is on, the current is flowing through the capacitor C1 and in the load resistance from negative to positive. So it means we will get a negative cycle over here as the current cycle or the current uh, direction changes. So in the first case, the current direction was from positive to negative. In this case, the current direction is from negative to positive. So we will get a negative cycle over here. After that, we will turn off S2 and turn on S1 again. So the current direction will same changes again. So we will get a square waveform with positive and negative cycle, positive and negative cycle. Its duration depend upon for how much time the S1 is on and for how much time the S2 is on. So the output RMS voltage is V out RMS divided by Vs divided by 2 by using Fourier series. So this is the waveform that we are actually this is actually the signal or that are actually provided to the S1. So if this is a firing pulse, so if it's a firing pulse, so this firing pulse will be provided to the S1 thyristor, the T1 thyristor that can be used in place of S1. So its turn on timing will be from 0 to T by 2 second. But if in this time after that we want to turn on the S2 switch, so what we will have to do, we have to provide a gate firing pulse to the thyristor T2. So this will be the shape for the thyristor T2. So this type of the gate firing pulse will be required for the first thyristor that can be used in place of S1, and this type of gate firing pulse is required for the S2 thyristor that can be used in place of T2, that can be used in place of S2. So this will be the shape of the firing pulses. This will be the output voltage that are actually we are getting through the uh, through the load port, through the load, and it's for the resistive load. If the load is resistive, so this type of output waveform will be observed on the oscilloscope. So what is fault and dead time? And practically the dead time as shown below is required to avoid the shoot through fault in short circuit across the DC rail. Dead time creates low frequency envelope, low frequency harmonic emerges. This is the main source of distortion of for high quality sine wave inverter. So what actually happens if the current flows, so this is the short through fault that a large short circuit current flows through the switches. So what actually there arises a dead time. If the gate pulse or the gate duration are disturbed, so this is S1 and this is S2. So it means that the S2 is off at this time, but it is on at this time. So there is a small gap between that can also be known as dead time. So if this dead time arises, it means that both the switches are turned on at the same time. So what will happen? A short circuit current will flow through this. So in order to avoid this, we have to do what? We have to provide specified uh, gate pulses at specified time, so that no that the case of that the case that both the switches are on at the same time did not appear. So what we have to do, we have to be very careful in this matter, that the that no that both the thyristor are not turned on at the same time. If both the thyristor turn on at the same time, a maximum or a short circuit current will be flow through this. But we have to avoid it, and we have to select the switching time such that when the S1 is on, the S2 is off, and when the S2 is on, the S1 remains off. So this is also known as short through fault, or the time in which this current flow is known as dead time. Okay. So first of all, single phase uh, full bridge inverter. So this is a single phase bridge inverter. DC supply is over here. This is one. Four switches are used. These switches can be thyristors, can be MOSFET, but they should be control devices. So how they actually operate? They actually operate is that first of all, in the first case, what we have to do, we have to turn on the S1 and the S2 switches. So what will happen? The DC voltage, the current will flow through the S1, through the load resistance, and through the S2, and will complete its path. For the next cycle, we have to turn on the S3 and the S4 switch and turn off the S1 and S2 switch. So when the S1 and S2 turns off, the current will automatically flow through the switch 3 and switch 4. But this time, in the first case, the current was flowing from positive to negative, but in this case, the current will flow from negative to positive. So the full bridge is the built-in form of two half bridge legs. Uh, Already, it can be built from two half bridge legs. Switching in the second leg is delayed by 180-degree from first leg. So what will happen? So when the switch 1 is on, so this type of output waveform is actually appear over here. So when S1 is on, we have to turn on the S2 as well. So what will happen? What will happen? The current will flow through this path. So we will get a positive cycle. When we turn off S1 and S2, we have to turn on the S3 and S4 at the same time in order to avoid the dead time. So S4 turns on and S3 turns on. So when these both turns on, the current will flow, and the current direction in this case will be from negative to positive. So we will get this type of output waveform. So this was the case when the S1 and S2 on, and this is the case when the S3 and S4 is on. So this is actually what? This was actually a single phase bridge inverter. Okay. So H bridge basis creating actually DC AC from DC. Uh, this is actually an so this is actually diodes are used over here, and this is actually a load. So either a plus or a negative is closed. So if a plus is closed, so we have to close the but never end. Either a plus switch or a minus switch is closed, but never at the same time, or either B or B negative is closed, but never at the same time. Same time closes would evaluate to short circuit from DC voltage to ground. To avoid short circuit through using real switches, there or turn on and turn off delays a dead time or blanking time is implemented, corresponding to values of VA and VB. So when a plus is closed, VA voltage will be equal to VDC, and when a minus is closed, VA voltage will be equal to 0. When B plus switch is closed, VB voltage will be equal to VDC, and when B minus switch is closed, the voltage VB will be equal to 0. So these are the corresponding voltages of VA and VB. Okay.
Yes, sir.
ओके नो एच ब्रिज इन्वर्टर यहाँ तक क्लियर है या नहीं ये बता दें इन्वर्टर की
जी सर.
अच्छा okay now H bridge inverter so inverter actually transform the DC to AC uh, depending upon the load over here. If the load is resistive, then there is no need of the diodes over here. But if the load changes to inductor, then there is a need of diode in order to allow the current changes that has actually arises from the inductor. So the voltages over here was DC corresponding to values of AV when a plus switch is closed. When a plus switch is closed, the B minus switch is closed, what will be the voltage? So when this switch is closed, the voltage will here will be plus VDC, or if you are observing voltage over here. So this will the first case if there are thyristors over here, so we have to turn on this thyristor and this thyristor at the same time, we will get a positive square waveform voltage over here. But when the A plus switch is closed and B plus switch is closed, what will be the case? So the case will be can be observed through this emanation. So okay. So when the freewheeling diodes permits current to flow even if all switches are open. These diodes are permanent lagging current to flow in inductive load. So why I have mentioned this already that if we are using inductive loads, then diodes are required over here in order to. But if we are not using any inductive load and the load is resistive, there is no need of inductor no need of diode over here. So these freewheeling diodes permits current to flow even if all switches are open. And where if the switches are open, where will be the current? There is a current, and which current? The current that is through the that is actually that arises from the uh, inductor load. So due to this, there is a need of a path for the current, and this current is actually provided by the diodes over here. So these diodes also permit lagging currents to flow in the inductive loads. Now the next case is, so if the switch, this switch is closed and this switch is closed, B plus, B minus switch and A plus switch is closed, the voltage was VDC. Now the next case is when the A plus switch is closed and the B plus switch is closed, what is the voltage over here? There is no voltage here. As why there is no voltage? Why there is no voltage over here? For this case, when the S plus switch is closed or and B plus switch is closed, the VAB voltage is equal to 0, the load voltage. Okay. So the next case is when the B plus switch is closed and a minus switch is closed. So we will get a voltage of minus VDC in that case. And for the third case, when the B minus switch is closed and a minus switch is closed, the total voltage will be 0 volts. So if we combine, so this was the first case when both switches are closed. Then this is the second case when the both switches are closed. So we will get this type of output waveform. So this is actually a square modulation type. We will get a square type of output waveform from this type of inverter. And this is the case for the inductive load. When the load is inductive, so this type of circuit is used and this type of output waveform is observed over here. So if the switch 1 and S2 are closed, we are getting positive voltage. When S3 and S4 are closed, we are getting a negative DC voltage. And for other cases, we will get 0 DC voltage. So with an inductive load, I is delaying beyond the voltage VL through the voltage wave still a square. At steady circuit condition, the current wave shape become repetitive. The current will grow an exponential during the positive half cycle up to the IP. So this is actually the case. So this is actually the output voltage. This is the output voltage that we are getting from this type of the circuit is this its shape is like that. But the current shape will be different as the load is inductive. So the current will rise exponentially in this case. It will exponentially rise from negative to positive and from positive to negative and for this case. But if in this if the circuit is the load is resistive, then the output current waveform will be equal to or will be same like the output voltage waveform. But in case of load is inductive, the current waveform will exponentially rises and exponentially decaying. So what we have to do now, it's a sensitive case. The sensitive case is like that we doesn't know or the circuit doesn't know when this zero crossing will be occur. As if we are observing over here, so in this case, this current negative current is flowing through the diode D1 and D2. But as it crosses the zero, this current flows through the thyristor T1 and T2 up to here. Up to here, this waveform becomes negative, this output voltage become negative, so the current decreases, but this decreasing current flows through the diodes D3 and D4. After that, when it become negative, so this current then flows through the thyristor T3 and T4. So there is a zero crossing from negative to positive in this case, in this cycle, and there is a zero crossing from positive to negative over here in the negative cycle. So we doesn't know where exact this crossing occur. So if we are using thyristors as the switches, what we have to do, we have to provide we have to provide it what we have to provide it a succession but a succession of pulses, a continuous pulses from 0 to t by 2, that whenever there is a zero crossing, there is a pulse over here and it will turn on the thyristor. And same, we have to provide it negative succession of pulses for the thyristor T3 and T4 for half of the cycle. That whenever there is a switching, uh, there is a need of for the switching of thyristor, a pulse is over here. Suppose if you provide a pulse over here, but there is no thyristor, but there is no need of to turn on thyristor over here as there is no current or no current is provided to thyristor over here. So the thyristor will remain turns off. But now if we turn on the thyristor over here, so the waveform shape will start from here. But we need it that this actually that the gate pulse should be provided at the exact location, but the exact location is not defined. So what is the solution? The solution is that we have to provide it succession of pulses, a continuous pulses from 0 to t by 2, that whenever the thyristor want to turns on, a pulse is a pulse should be over there and it will turn on these thyristors. यहाँ तक समझ आ गई इसकी या नहीं?
Yes, sir.
Okay.
سر جی حمزه دغه کوی زما وی سجی نیټ کې مسله راغله وی سر ته وی دغه کوی زما आवाज
سوکو چیٹ چلتا ہے. हाँ, अच्छा नेक्स्ट हमारे पास है, so this is the output voltage that is actually we are getting from the simple square inverter, and this type of exponential growing waveform is or instantaneous output waveform of current is actually observed on the oscilloscope. So these are the waveforms of the output voltage and current. So inverter output voltage, so this type of inverter, this is the output DC voltage of the inverter. The output voltage will be alternating voltage A square wave shape for either or L load. So if the load is resistive or inductive, the output voltage will be like that, but the current will change. The current waveform for inductive will be like that, and it will be in shape of square waveform for in case of resistive load. So what we have to do, we have to harmonics. There are different harmonics, different types of harmonics. They are combined, they form what? A square waveform. So in square waveform, there are different types of harmonic, like harmonic number 1, 3, 5. So for example, this is the first fundamental harmonic. So when it's combined with third harmonic, this type of waveform is observed. When it combined with the fifth, seventh, so when different types of harmonics are combined and all of them are odd harmonic, so a square type of waveform is actually formed. So what we have to do? So harmonic effects on induction machine. So 1, 7, and 13, they produce positive sequence, and 5th, 11, 17 harmonics, number harmonic, they produce negative sequence. So triple harmonic 3, 9, 5 produce zero sequences actually. So this is actually the effect on the harmonics effect on the induction machines. So output voltage harmonic distortion. Harmonics causes distortion on the output voltages. Lower order harmonics are very difficult to filter due to the filter size and high filter order. They can cause serious voltage distortion. Harmonic reduction can be achieved by filtering or using harmonic elimination techniques. What are the techniques? Uh, why need to consider harmonics? Because they causes power quality issues. Harmonics may cause degradation of equipment. Equipment needs to be derated. Total harmonic distortion is the measure of determination of the quality of given waveform. So what is its solution? A Fourier series is used for it's the analysis tool for different waveforms. Fourier series actually it consists of DC terms and a cost terms and sine terms, and Fourier it's the Fourier inverse. So what we have to do? We have to apply Fourier series on this square waveform, and we have to extract different harmonics from it. A0, An, and Bn. So we will calculate all these harmonic where n is the even number and cos n where Bn is even harmonics doesn't exist. So for square waveform, there are no even harmonics over here. And the odd harmonics value is equal to 4VDC divided by 2 pi. So for square waveform, this is the spectral waveform, spectral representation of here, that the first harmonic, fundamental harmonic value is like that, the third harmonic, fifth harmonic. So it's represent that what are the different harmonics that are actually present in a square waveform. So the harmonic decreases with the factor of 1 by even harmonic or absent. And the nearest harmonic is the third harmonic. If the fundamental is 50 hertz, the nearest harmonic is 150 hertz. Due to small separation between the fundamental and harmonic, output low pass filter design can be very difficult. So what we have to do now? We have to do, so this is the fundamental component, this is the third harmonic, and the other one is fifth harmonic. So these are the its RMS peak values and RMS values of voltages, currents, and powers. So now AC voltage generation. So this was square waveform. This was the output for square waveform. It's if we apply filter over here, we can extract the fundamental component, the third harmonic, and the fifth harmonic from it. Now, what is harmonic filtering? But we have to filter the first harmonic. So this is the DC supply. This is the inverter. Inverter actually what convert the DC supply into AC. This is a low pass filter is used. What will it do? It will filter. This was the output before filtering, and when the low pass filter is used, and when it filters the, and when it filters the ripples. So it will extract the first fundamental harmonic, and after filtering, we will get this type of output waveform shape. Now this is actually a pure sinusoidal waveform, and this is actually the requirement of DC voltage. So these are the steps that are required in order to filter the square waveform. So output of the inverter is chopped AC voltage with zero DC component. It contains harmonic. The LC section, what does the LC section does? The LC section, a low pass filter is normally fitted at the inverter output to reduce the high frequency harmonics. So in some applications such as UPS, high purity sine waveform output is required. Good filtering is a must. In some applications such as AC drive, filtering is not required. So if we are using like in the house appliances, if UPS is used, so high sine waveform output is required, because if there are ripples in the output waveform, so it can damage the house appliances, or it can damage the household components like lights or fans, etc. Now, voltage source inverter VSI with variable DC link. So DC voltage is varied by a DC to DC converter or control rectifier. It generates actually square waveform at the output voltage. Output voltage amplitude is varied as DC link is varied. So frequency of output voltage is varied by changing the frequency of the square waveform. So this is actually a VSI voltage source inverter. This is actually the output is DC, and this is a DC link. So what will this DC link produce? This DC link will produce a variable DC, a variable output voltage. If we want to vary the amplitude of the output voltage, what we have to provide? We have to provide it a DC link over here. So the output amplitude is varied as the DC link is varied. So if we change the value of capacitor, the output variable outer amplitude will be varied from at, through this type of inverter. So what are its advantages? It's a simple waveform generation. It's reliable, and the advantages are extra conversion stages required, or poor harmonics are required. Okay, so voltage, variable voltage or variable frequency compatibility. If we have higher input voltage and higher frequency, and in the second case, the red line shows the higher input voltage, higher frequency, and the green line shows the lower input voltage and lower frequency. So the output voltage can be varied by a period of square waveform pulse. Output voltage amplitude can be varied by varying the magnitude of DC input voltage. Very useful as variable speed induction motor drives. So we can vary the input voltage amplitude, and we can vary its frequency also from and we can vary it through by changing the magnitude of the DC input voltage. So VSI with fixed DC link. If the VSI is used with fixed DC link, when the DC voltage is held constant and it's not varied, so output voltage magnitude and frequency are varied simultaneously. They can be used. They can be simultaneously varied by using a PWM technique. That's actually pulse width modulation technique, and this technique is normally preferred as this. This has good control on the harmonic, but it's expensive as of complex waveform generation. So this actually the problem with this type